Who's the author of that?
Yeah, do electric sheep have dreams?
Henline, no.
Yes. Great. Well, I'm really happy to welcome everybody to the second day, sessions 4, 5, and 6 of our third Unither conference on nanomedical and telemedical technology. My co-chair, Dr. Baruch Blumberg, will be providing our keynote opening remarks this morning, and will also be managing the conference schedule during the rest of the day. Dr. Blumberg has had a most diverse and illustrious career advancing the cause of medicine, science, and field biology. I will start with what I think is the most astonishing achievement, and that was his discovery of the hepatitis B virus and work on the hepatitis B vaccine, which the United Nations has attributed to saving the lives of hundreds of millions of people. The hepatitis B virus is one of the most endemic viruses in humans that exist, and has some pretty awful sequelae if it proceeds untreated. So it would be really hard to contribute more to our species than Dr. Blumberg has with that work alone. But that's really just one part of his wonderful career. He's done field biology research throughout the world, coming up with numerous exciting discoveries that have advanced both natural science and medicine. He is on the faculty of the Fox Chase Cancer Center as a distinguished advisor to the president, oversees a number of different cancer therapy opportunities there and advises Fox Chase Cancer Center on those. Just recently, he was the director of the Astrobiology Institute at NASA, based at Moffett Field, in charge of efforts aimed at identifying very early life forms of extra-terran nature, ranging from activities in radio astronomy to identify molecular precursors to life forms in deep space, to efforts with the Great Planetary Explorer program, which, as all of you know, has searched for life on Mars and is searching for conditions conducive to life in the atmospheres and on the surfaces of moons of other planets in our solar system. Dr. Blumberg is also the chairman of the Scientific Advisory Board at the sponsoring company here, my company, Unither Therapeutics. And as chairman of the Scientific Advisory Board, he helps guide our company's research into cardiovascular, oncology, and viral disease treatments. So this is just a short summary of Dr. Blumberg's great career, and it's my immense honor to be his close friend and colleague and to welcome him to the podium to provide us with the opening keynote remarks.
Thank you, Martine, for that very kind introduction. When I was last week preparing what to say for this event, I went through the schedule and decided that I'd like to address a few kind of general medical issues, medical and public health issues that pertain to the eventual use of nanotechnology. It's obvious from our talks we're at a very early stage of the field, and later today we're going to hear from the inventor of one of the first nanotechnology projects. So there's a great kind of future ahead. And it's a very interesting intersection between biology, medicine, life sciences, and engineering. And it's interesting to contrast the different approaches that engineers have to that which biologists have. Biologists are immersed in in many ways, very different kind of system. Engineers have a different approach based on believable physical laws, whereas in biology we have a little problem coming up with general laws that pertain all the time and everywhere. We tend to be a little more statistical, probabilistic. Now, the biological systems have, in a way, been defined as systems in which you have diversity and then selection and evolution. And life matter has a genome, the human genome, for example, which has a great deal of conservation in it. That is, many of the genes in our genome, 70, 80% perhaps, are strongly conserved. That means we contain within our own genome genes that are very similar to those that archaea had. That is one of the most primitive forms of life that shares about a third of its genes with humans. That's really quite remarkable. And it's these genes, the conserved and occasionally introduced new genes, that are the subject, it's the material on which evolution is based. That is, when changes in the genome required because of changes in the environment, they select these ancient genes. It's really interesting to question why we've retained all those. And you can't help feeling that if in the explanation of how this might happen is that if we can't predict what happens in the future. So we have genes that are prepared to deal with an unknown and unknowable future, but which reflect much of which happened in the past. Makes you think there's a kind of cyclic character to events. But in any case, the genome and consequently the phenotypes, the things that make processes work in biology, is not built for efficiency at any given time, because it retains these genes and therefore the products of the genes that may be useful in the future. So we're less than fully efficient. On the other hand, engineers want to design devices that are highly efficient. And they have everything that they need, but not much more for what they don't need. There is some evolutionary thinking in engineering, but the kind of time scale we're talking about precludes a great deal of concern about that. So biological systems are a lot less efficient than engineers would like them to be. There's always this remark that if I had to do it, I'd do it another way. And that may be quite true, but that doesn't take into account the great time depth where that happens in the evolution of species. Now, there's another feature of designing therapeutic diagnostic methods which kind of looks at the potentially the putatively affected population, as the people who get the drugs, as homogeneous, whereas everyone knows they're not. And this issue has really come to the fore in the last decade or so because of our greater knowledge of the genome. And we recognize that there's enormous variation within the genome. Much of that is now recorded in the SNPs collection. Those are collections of polymorphisms. That is sections of the genome where variation can occur or does occur. And those SNPs, polymorphisms, are now widely used to determine differences between individuals that relate to susceptibility to disease and also different responses to drugs. So it's been, in my experience, very hard to get this well within the thinking of drug companies who don't like the idea that there may be certain parts of a disease group that are not susceptible to, that are not treatable by the drugs that it have. In effect, it kind of decreases the market. To my view, this is rather short-sighted because it means you can identify a portion of the population that is highly, will have a very good response to the medication. And then by presumably possibly some minor variations in the formulation or in the chemical structure of the drug in hand, you can make it better for the people who don't respond to the initial medication. So in all these therapies, we're thinking about the preventive measures, the treatments, devices. It's important to keep in mind that you can essentially say for any form of treatment or prevention, there'll be some people who respond and some who don't. When people are exposed to a infectious agent, let's say, some get sick and others don't. It's one of the most amazing, interesting aspects of medical science. And I spent the first, 20 years of my scientific research on that very issue. Back in those ancient days, and we're talking 50 years ago, we didn't have a genome to use to study variation, but we used the phenotype. That is, you could study certain proteins and look for variation. But instead of, and currently by examining the databases for the genomes, you can find 2 or 3 polymorphisms before T. But it would take 3 years to establish you had found a polymorphism using involved family studies and so forth, when we only have the phenotype to deal with. So again, it's very important to keep this in mind when thinking about any of the potential therapies that will come forward in the future. Now, another possibility of nanotechnology is very increased sensitivity. That is, you can detect abnormalities, potential abnormalities, at a very early stage. That's both good and bad. The fact is, for many diseases, many cancers, people may have indications of cancer at a very early age. And the argument would be to cut it out surgically or provide treatment for it. While it's known that many of these cancers may remain in the individual, may grow somewhat, but they'll die of something else. That is, the rate of growth is such that the competing risks, i.e. other diseases, will kill the person before you have to worry about the cancer. And what you don't want to do, if it's possible, is to fuss around, remove the cancer or treat the person if he or she doesn't require it. Now, a case in point, which many of us are more than mildly interested in, are cancer of the breast and cancer of the prostate. Now, in cancer of the prostate, there's a very interesting study that was done some decades ago, actually, in which autopsies were performed on people of, I think the age was about 80, who had died for reasons not from cancer of the prostate. And some 80 or 90% of these individuals had detectable cancer of the prostate. If they'd been examined during a lifetime and these had been seen, they would have been properly surgically removed. Well, what does that mean? That means there's a lot of cancers of the prostate you shouldn't do anything with because intervention can have negative consequences. Now, there's another interesting way to look at it. If you look at the data and you say that people who are over 80, 90% of them have cancer of the prostate, and people who are 4 or 5% would have it, and intermediate ages, there'd be some intermediate number. So one way of looking at that is to say that it takes a long time for cancer of the prostate to become detectable. Another equally logical hypothesis is that getting cancer of the prostate increases your longevity. Now, we don't often think of cancer as a kind of beneficial thing, and I'll show you why I don't. However, something that's that common, that is under the influence of these polymorphisms, may have advantages. Now, we don't know what those might be, and the main reason we don't know is very few people look for them. However, one of the consequences of the relationship of disease susceptibility to these polymorphisms and the diseases occur in high frequency is that there may be beneficial effects. I'm sure that's not going to deter any of you from your pursuit of remedies for the cancers and other diseases, but I think that it's well to keep this biological possibility in mind, this concept of polymorphisms in which diseases that are affected by polymorphic traits are likely to have beneficial effects. The thing that we all learned in high school biology was the sickle cell trait and protection against falciparum malaria in young people. There was a balance in the advantages. Now, another point that I'd like to raise, and that's come up from time to time in our discussions so far, and today as well, is the issue of targeting cancer cells. Now, much of cancer therapy is based on the idea that there are cancer cells and there are normal cells, and we'd like to get a quotation marks from 2 centuries ago, a magic bullet that only affects the cancer cells and doesn't affect normal cells. That hasn't happened. And the likelihood of that happening, I think, is small based on prior experience. And a lot of that's due to the fact that cancer cells are our cells, and they're very similar to our normal cells. They're us. So a war on cancer means you're having a war on yourself. and you want to be cautious when you do that. So that constantly raises the issue of therapeutic index. And sadly, a lot of chemotherapy is based on very small advantages. There was a drug recently approved by the FDA, and there was a trial, a very well-designed trial, in which the therapy that was existing, if the treatment, survival after treatment, initiation of treatment after diagnosis, was about 9 months. And this new drug, which had every possibility of being $1 billion drug, increased life expectancy to 13 months. And drugs that have that level of improvement are considered to be highly successful cancer drugs. Now, if I suffered from one of those cancers, I think I would take that drug despite the minimal improvement, and there's always the hope that we'll get better and better, and that has happened. There's just been a recent survey that indicates there's been some successes. But treating cancer can be very difficult, and it's much better to prevent it. And also, it'd be good to get therapies that aren't dependent on killing cancer cells and therefore killing normal cells. There's an attempt to do that, trying to get medications that affect the cancer genes. Gleevec is an example of how this may be the case. But Gleevec works in a relatively small number of cancers, unfortunately. And then the possibility of altering the immune system on the notion that there's a kind of immune surveillance. If you can kind of get that better, then the cancer will be under control. Well, again, those applications, there are some, but they haven't been overly dramatic. Now, I've worked on hepatitis B virus for many years, and we invented a vaccine that has been amazing, successful beyond my hopes. And since about 80% of cancer of the liver is due to hepatitis B virus, the vaccine program that's been in place for 20 years or so has now shown a significant decrease in the incidence of cancer of the liver. So prevention of a cancer is far better than treatment. And the big successes in our campaign against cancer, the war on cancer, you might say, has been a consequence of preventive methods. That's been the major improvement. And it's been estimated some 20 or 30% of cancers are associated with viruses, and the number may be actually larger in the sense that viruses may have some role in addition to other etiologic agents. Nothing is ever caused by one thing. There are always multiple causes. Well, so this vaccination program has greatly reduced the number of cancers that have happened and that we can expect in the future. And there's another vaccine for papillomavirus that was introduced 3 years ago, and vaccination programs are have started for a few years now. And the hope is that also will lead to a decrease in a very common cancer of the cervix and certain other cancers that are rare. And I think it's very valuable for cancer research institutes to spend more time looking at viral-caused cancers. Now, another aspect of this is that the people who get cancer of the liver are often infected about the time they're born, and they remain asymptomatic carriers of the hepatitis B virus for decades and develop cancer of the liver in their 40s, 50s, and 60s. So that means you have a 40, 50-year lead-up time when you can do something. Well, you don't want to start treating a kid the year he or she is born, or you want to delay it as long as you can, as a matter of fact. But there's now quite good evidence that if you lower the titer of the virus, you don't have to get rid of it. It's very hard to do that because the virus is integrated into the host's genome. But if you lower the titer to some sort of acceptable level that's been defined, you greatly decrease the risk that the individual will get cancer of the liver or chronic liver disease. My guess is that will prove to be true for papilloma infection, that is for people who did not receive the vaccine and go on to, and therefore have a risk of getting cancer of the cervix, or in the case of hepatitis, cancer of the liver. And it also means you don't need a very good drug, because if you have a drug that, or you can use a good drug in lower dose, and this is a totally different approach to the treatment of cancer. You're trying to deal with a virus or a virally infected cell, and not use a therapy that has these unfortunate side effects by attacking and killing normal cells. So those are some of the other some of the general statements I wanted to make. And later on today, we're going to hear some papers on systems biology. Engineering approaches tend to be very direct. A great example is you want to go to the moon. Well, you can go outside on most nights and you can see the moon. You actually can see your goal. But very often in basic scientific research, if you wanted to discover new things, then what you don't want to know to start with is what the goal is, because that's something you already know. And what you want to do is discover something nobody ever knew about. So how do we, but in applied research, we're very keen on getting from Earth to the moon. We're very keen on making a particle of a particular dimension that has certain binding characteristics that will direct it to a cancer. And if you make some observations en route that are not part of the pathway, are not part of the benchmarks that you have to pass, you are cautioned not to take and look at those things. Well, that's not what companies should do, and not what companies should go to the goal. But academic scientists are the ones who are in effect paid by the taxpayers, by the government, to do basic science and to investigate these things. So the important part is that if we continue to apply what we know, we're never going to learn anything new. We're doomed to continue in the same process. But if we can learn that we should be able to follow directions that are piqued by our curiosity, or that emerges along the path of application or to reach a very well-defined goal, we should have there should be something in the system that allows that to flourish. Well,